All right, guys, why don't we get everything started here? I'm Brian Hesterman, Chief Operations Officer for InSpire Transpiration Solutions, and I'll be the moderator of today's presentation. We really appreciate everybody joining us to discuss the 10 cardinal parameters of plant health and vitality. This is the beginning of a webinar series that will set the stage for deeper dives on specific parameters. Based on the diversity of our audience, we'll likely go too deep for some and not deep enough for others. We invite you to join future webinars, which will shape this series into a much deeper understanding and appreciation for cultivating cannabis. Our intention is to share some information that we, researchers, and other industry professionals in our ecosystem have collected and applied to large-scale cannabis cultivation facilities to minimize cultivation risks and maximize genetic expression. As the title of our webinar suggests, there are 10 parameters that work in symphony to produce an end product that contains and preserves all of the secondary metabolites, which consist of cannabinoids, terpenes, and flavonoids that are of value for recreational and therapeutic cannabis products. The structure of today's webinar will consist of a 30-minute presentation by Jesse Porter, InSpire's Cannabis Business Specialist, and Robbie Batts, InSpire's Chief Technology Officer. Together, they possess decades of experience and a deep well of knowledge on how engineering can best impact plant physiology in a controlled environment. This professional intimacy has spurred a passion across the entire InSpire team to deliver equipment and control systems that allow cultivation facilities to independently control temperature and relative humidity, maximize canopy airflow, and provide the environmental data and plant itineraries to reward investors and owners with optimal carbon capture and photosynthetic outputs. The presentation will be followed by a 20 to 30-minute Q&A session. Please feel free to ask questions as they come up during the webinar, and we'll do our best to address as many as possible. With that, I'll pass it off to Rob to kick us off.
Thank you so much, Brian. Today's talk is truly inspired by Dr. Bruce Bugby's presentation at the CGC in Niagara Falls in late 2019. His sectioning of the main inputs into 9 cardinal parameters is something that brought us to the realization that all of the systems of plant growth are intertwined in a way that it's impossible to focus on one without having an impact on perhaps several others. So why do we have 10 and the esteemed Dr. Bugby has 9? Well, Dr. Bugby was specific about his 9 parameters being environmental only. We are humbly adding a 10th, which is microbes, because our conversation is specifically general plant inputs around cannabis. We've seen its impact on the high dollar value of the cannabis plant, and we would be remiss if we did not include them. We find that when most people talk about growing environments cannabis, they're most often looking for that nugget of wisdom as it pertains to VPD. And many of you probably joined for just that reason. Well, we don't blame you. It's a topic we take most seriously as a company that is built on a backbone of temperature and humidity control equipment and controllers. We're going to do a deeper dive shortly, but to set the stage, let's talk about it right here. VPD is vapor pressure deficit. It is water vapor pressure deficit. And our business at InSpire has become control of this very important metric by designing efficient systems that control, track, and trend the metrics. Some amazing things happen when you get it right, and we've seen some less than desirable things happen when you get it wrong. We take our job of dehumidifying and conditioning the air very seriously, because without some place for water to move from inside the plant to outside the plant, it would be impossible for plants to thrive. And at the end of the day, that's our business. Now, it's almost a true. It's important to both leaf temperature control and the photosynthetic process, amongst other things. But the real understanding that plants only use a small fraction of the water you give them is the start of a deeper understanding to environmental controls. See, water is pulled through the roots, up the stem, into the leaves, and would otherwise have no place to go except for the fact that there are tiny pores in the plant called stomata through which the water can escape. Now, these pores are mainly where CO2 enters the plant, oxygen gas leaves the plant, and also the water that entered the plant through the roots as a liquid evaporates out into the environment. Now, in order for the liquid to evaporate into the air, the surrounding air must be below the saturation threshold of water. Taking a closer look at the picture on the left that you're going to see again and again and again in this presentation, you can see that there is a substomatal cavity just on the inside of the stomata. The entire gas exchange process I mentioned in the previous slide, well, that happens here. And if the surrounding air is moist, there's a good balance of CO2 entering and H2O leaving the plant. If the surrounding air is too dry relative to inside the plant, the CO2 has a hard time fighting its way upstream from all the water vapor leaving the plant. Now that that's out of the way, let's talk about the interplay of all these variables in the context of plant vitality. Jesse, take it from here.
Hey, thanks, Rob. Great information there. And I think diving into the parameters of plant influence, they're a wonderful reference point for understanding the interactions that maximize the plant's vitality and directly influence VPD. These cardinal parameters work synergistically to create the ideal cultivation environment. And as we collect more data, we might even uncover more parameters of influence. Hormones, maybe? I don't know. But for now, we'll talk about 10, many of which you're probably familiar with. Light, humidity, temperature, CO2, and airflow. And then down in the root zone, we have temperature again, nutrients, microbes, oxygen, and water that are all major influencers in plant health. But what plant, right? Cannabis, sure, but understanding the genetics and breeding history of a cultivar can have significant influence on our environmental set points. When I speak on genetics, it's very easy for me to show you pictures of beautiful strains automizing, expressing unique traits, and oozing their oils. But I think it's even more powerful to share a concept from Robert C. Clark and his book, Marijuana Botany. As you can see in the diagram, phenotypes are the byproduct of genetics mixing with the environment. Makes sense, right? Strains are bred to thrive and are uniquely adapted to the environments in which they're created. So whether you're growing a maple leaf indica from a reputable seed breeder, a landrace Vietnamese black you picked up on vacation, or a handful of beans from a friend, it can be very helpful to understand where they came from and how they were bred in order to let them sing. If you think you're trying to create the perfect conditions for your genetics, you should first consider the habitats associated with the genetic origin, and then follow the environments in which it was developed in order to get the most out of your phenotype. So with genetics considered, let's take a quick look at light and its powerful and dramatic interaction with the other plant parameters. In order to maximize photosynthetic rate and your lighting investment, right, it's important to harmonize temperature, CO2 levels, and ppfd while thinking about your lighting source. As you will see later, there are separate VPD charts for LED and HID lighting. This is because HID lighting emits radiant heat, which impacts the plant and leaf temperature. As a result, the same plant will prefer a lower temperatured room for HID for maximum production and a higher room temperature in an LED room. Maximizing the photosynthetic rate of cannabis requires a keen understanding of the relational set points associated with your lighting choice. And as mentioned, there's also a relationship between light and CO2. We know plants use light energy to convert CO2 and water into sugar and oxygen. It's photosynthesis, right? But we also know as light intensity goes up, the amount of CO2 utilized by the plant does too. CO2 is a plant food that passes through the stomata and is necessary for the photosynthetic process. And the amount of CO2 assimilation is directly related to the accumulation of plant biomass. So when you consider parts per million of CO2, you should correlate that to ppfd and the stage of plant growth. As the plant transitions from clone to veg to flower, CO2 can be increased alongside light intensity in order to maximize the plant's development. But what good is CO2 if you can't deliver it to the plants effectively, right? Airflow has a direct impact on how CO2 is delivered to the stomata. It also affects the leaf temperature, influences stomatal reactions, microclimate management, and VPD. In cannabis plants, the stomata is on the undersides of the leaves. So the most efficient way to deliver conditioned CO2-rich air is up through the canopy and directly to the undersides of the leaves. Now, as air passes the leaf surface, it has a drying and cooling effect that should be accounted for when determining room conditions and leaf temp. Airflow considerations are also imperative to a successful harvest, as it can break up canopy overlap, contribute to cultural control, help mitigate odor. It can even impact drying and curing, employee health, and overall IPM strategy. Airflow also plays a part in successful regulation of temperature and humidity. And on that note, I'll pass things back to Rob, who can talk about what happens when we get hot and wet.
Thanks a lot, Jesse. At InSpire, we've spent almost a decade trying to understand the interplay of temperature and humidity and its influence on plant metabolism. You know, it turns out that when water evaporates from inside the substomatal cavity that I talked about before, it has the same effect as sweat leaving a person's skin. It'll cool the plant down and make the environment around it more moist. Now, the rate at which this happens is very important because the leaf has a somewhat narrow band of temperature where the chemical processes are most efficient. Efficient chemical processes inside of a plant mean higher yields and higher revenues. So if we measure this for a plant, it should be easy enough to just set the room temperature to the leaf temperature we want, right? And bingo, increased yield. Unfortunately, that's not the case. Although some days I really wish it was that easy. Instead, all sorts of variables affect leaf temperature, and leaf temperature is almost always not room temperature. Now, it's not exactly easy to measure this effect because leaf canopies are not a single temperature, as you can imagine. And in fact, they vary even across a single leaf. Now, in practice, the room is easy to measure. We set up an array of aspirated sensors inside or close to the leaf canopy and take our readings. But to understand the leaf temperature, most often we use an indirect measurement via, for example, a thermal imaging system. Now, it's important to remember that the primary heating source for a plant is the radiation that is absorbed by the leaf. And this comes from primarily two different sources. Now, in a room lit by HPS lights, we have the lights themselves that are throwing infrared photons into and through the canopy. Essentially, we have a source of heat similar to a microwave, heating the leaf from the inside out. Now, most LED lit rooms don't have this energy source. To maintain the correct leaf temperature, we have to bring heat to the plant by elevating the room temperature around it, and the walls and the surfaces provide some infrared input to heat the leaf up. And further, we'll use convection and warmer air inside the room to keep that leaf in the narrow band I mentioned before. Now, this might be a topic of a webinar in and of itself, but if you want to jump ahead, maybe hop onto Google and study the Bowen ratio. Now, this defines the amount of energy a thermal outputs and heat loss through the transpiration process. Now, speaking of which, remember when I told you before that we need some sort of lower moisture environment so the plants can transpire and the water can move through the plant? Well, that's true, but let's talk about humidity in a different context. Let's talk about the pests that thrive in humid environments. Now, we're going to be showing you some tables later that indicate a good humidity relative to temperature for different stages of growing environments and growing rooms. And this might lead you to believe that anywhere inside those ranges is good for plant health. That may be considered true, but for the most part, inside of a room where we are moving often hundreds of gallons of water through the air, we have to be careful not to give the pests a place to thrive. Now, it's widely understood that humidity has a direct impact on things like powdery mildew and botrytis. Keep this in mind. The general rule of thumb is the wetter the room, the higher the likelihood that even a small outbreak of these pests can become unmanageable and revenue destroying. So what about the plants now and the effect of humidity on them? When we look at this leaf cross-section, we have to remember that in order for the plant to use and move water, we need to have a humidity level outside the plant that is less than inside. This difference is literally sucking the water through the plant. This difference is VPD. Now, it's actually a fairly simple task to get an appropriate VPD chart if you know just 3 of the things I've already mentioned. Get yourself over to the website you see in the bottom right-hand corner with your room temperature, your room humidity, and leaf temperature in hand. And voila, you can generate a VPD chart for almost any type of growing environment, assuming that the chart is drawn for whatever plant you're growing with. But don't forget, lighting type affects how the chart is drawn. The chart below might be the kind of chart you'd use in an LED lit room, and this is the kind of chart you would find if you're using an HPS or CMH lit room. Notice that the corresponding good areas of transpiration have changed. Well, let's make things a little more complicated. As you can see from this chart, on the right-hand side, a plant will photosynthesize less and less as the VPD increases, that is, as we make the environment drier. But as we decrease the VPD, make it more humid, the photosynthesis will increase, but so does the ability of a pathogen to thrive. There's a balance in there somewhere, and understanding that is going to be really critical to understanding how you can maximize the plants in your facility. Now, remember when I told you that leaf temperature is not room temperature, and that we had to use different types of measurement systems for both types of temperatures? Well, let's see how really, really complicated this can get when we look at a 15-hour leaf and room temperature trend in one of the rooms that we've put plants in. As you can see here, things change dramatically. If I wanted to take a look at just this differential, you can see here that the difference between the leaf temperature and the air temperature changes almost minute by minute. The peaks on the left and right-hand side indicate areas when the lights are on, and the value in the middle is when the lights are off. In this specific room, if you're trying to manage VPD with a static chart on the wall, you might have a hard time. Now, we use control systems and produce control systems that can measure temperature and humidity and plant temperature across an entire range of time, from the beginning of the plants being moved into a room to the time the plants leave. It's with these sensors and controllers that we're able to measure the moisture removal from the room every single day and feed that information back to growers who might find some useful nuggets out of that. What I'd say is we can see that the plants transpire more when the lights are on, and that's the blue bar on the right-hand side. At night, they transpire less, and in fact, most of that moisture is cuticular moisture loss. By adding the blue and the red bar up, we can tell you with pretty good certainty, plus or minus 5%, exactly how much transpiration is being sent through the room. Now, if you're going to start off by trying to control room humidity and VPD, you're going to need to size your equipment appropriately. We use the equation on the left-hand side as a starting point based on the data we've taken from rooms, and we suggest you do as well. Well, that's enough about temperature and humidity. Jesse, why don't you take it from here and talk about root zone temperature and the rest of the parameters?
You got it. Thanks again, Rob. So temperature is also a major factor in creating a healthy root zone. When it comes to the root zone, I think it's really important to consider the media and its role in root zone thermoregulation. For example, we know that soil holds its temperature differently than rock wool. And if you're thinking about an aeroponic approach, it's going to be heavily influenced by water temperature and room conditions. Now, root zone temps play an important role in nutrient uptake and root exudate production. For example, studies show us that root zone temps higher than 77 degrees inhibit the uptake of calcium and other nutrients. And a root zone that is too cold will slow chemical reactions and lessen the plant's ability to capture nutrients. A highly accomplished colleague of mine would say, finding the sweet spot for your genetics is about determining the temperature that balances enzyme and ion concentration in the root zone for maximum uptake. I like to say it's like Goldilocks. It's all about finding the right porridge. And when it comes to mealtime for your plants, we know there are many different nutrients and delivery techniques available to the cannabis cultivator. Many of us even have our own secret recipes. Despite that, one thing holds true for every successful nutrient regimen. It's directly connected to transpiration. Might seem like a stretch at first, but when you think about how mobile nutrients are moved by the plant and immobile nutrients are moved through the transpiration process, it becomes more clear. In order to maximize your plant's uptake of immobile nutrients, you must maximize the movement of water through the plant. Otherwise, the nutrients will never get where they're supposed to go. We can collect some great information on transpiration and plant nutrition. First, we can test the nutrients available in the media and use that as a baseline for comparing leaf tissue analysis from new growth and old growth on the same plant. If we discover immobile nutrients lacking at any stage of growth, we can assume we miss an opportunity to maximize transpiration and nutrient translocation. Now, oxygen is another very important plant influencer. We know oxygen is something that your plants give off during the process of photosynthesis, but oxygen in the root zone also plays a critical role in roots breathing, chemicals interacting, and good microbes breeding. Now, if the media becomes compacted or the roots grow in an anaerobic condition, the roots will suffocate. Chemical reactions will slow, and your plant's growth will too. An anaerobic root zone is also a breeding zone for pathogens that will negatively affect plant health. Oxygen, water, and temperature are all interacting factors. We know that cold water holds more oxygen, but you don't want to put ice water on your roots, right? It's about balancing this knowledge with your media choice, room conditions, plant stage, and other factors to make sure oxygen is allowed to function most appropriately. Oxygen also helps us create an environment where good microbes thrive and pathogens don't. There are many different microbes on this planet that directly influence cannabis. One example Rob mentioned earlier was the botrytis that's all around us. Preventing conditions for it to take hold involve appropriate dehumidification, integrated biological filtration, airflow considerations, and proper staff training. But there's also good microbes we should think about managing. Beneficial fungal colonies will thrive on plants' roots in an oxygenated environment. Root zone fungus like Rhizophagus irregularis provides sugars to bacteria as a reward for making nutrients available in the rhizosphere. Sounds relatively simple, but managing protozoa, nematodes, microarthropods, fungi, and bacteria can be a real challenge when oxygen levels are low and fungal and bacterial pests begin to take hold. Instead, it's more about creating an oxygenated rooting environment where good microbes can maximize nutrient uptake, stimulate growth, and protect against pests and pathogens. Good and bad microbes like bacteria, virus, and fungus can be controlled if the appropriate environmental conditions are maintained. And when it comes to thinking about an IPM strategy, every good IPM plan starts with cultural control, which prizes prevention over attempted eradication. Filtering the air, creating right air pressures, optimizing airflow considerations, appropriately dehumidifying, and maintaining conditions that are unsuitable for pests is cultural control. The ability to precisely control your cultivation environment limits IPM applications, limits labor hours, and it gives you the ability to change conditions for a short period of time in order to increase the efficacy of an IPM application. For example, raising the humidity for a certain IPM application to be more effective, or dropping the humidity to control a fungal spread. Either way, environmental considerations are imperative to the success of any IPM plan and application strategy. And speaking of success, water management is paramount to cannabis cultivation. There is no life without water, right? And Leonardo da Vinci said, "Water is the driving force of all nature." I like this quote because I've heard the taxi cab water analogy before. Water is the vehicle that picks up all the nutrients and moves them around. Water is the driving force for cannabis plants, both internally and externally. Water delivery must be treated to avoid the development of pathogens like Pythium, and temperature of the water must be considered as it will have an impact on root zone temperature and oxygen holding capabilities. Oxygenated water will help the root zone grow and aid in beneficial microbe growth, and appropriate water pressures will maintain and maximize plant growth, nutrient utilization, and phenotype expression. And we all know that water in the room is humidity that needs to be managed appropriately in order to prevent things like powder and mildew from destroying your crop. Instead, we suggest you apply the knowledge that you have about vapor pressure deficit and use water to maximize your plant's expression and biomass. And with that, let me toss it back to Brian.
Jesse, Rob, excellent work. Very, very nicely done. We'd like to point everybody to a link on our website that has an HVAC sizing calculator that will help determine how much moisture removal each of your rooms need to maintain ideal VPD levels. It's in the chat section, and it's also on the screen that you can see now. Please also be on the lookout for our next webinar entitled Curing Cannabis to Preserve Secondary Metabolites. Every presentation will be uploaded to our website to be viewed anytime. At this point, we'd like to answer some of the questions that came in from you all. Here at the top, one of our attendees asked, is airflow different than HVAC?
Yeah, I think that's a really good question. And I think when you think about airflow considerations for a room, sometimes we separate them from an integrated HVAC approach. But when it comes to conditioning the air in the room and redelivering it to the plant, they're tied together. Specifically, I like to think about airflow as, breaking the boundary layer and recreating some outdoor environmental conditions that put some, subtle pressures on the plant and remind them that we are Mother Nature. When it comes to the bigger HVAC conditioning aspect, it's about removing the water that doesn't need to be there, and controlling the environment in a way that we're filtering biological pathogens and we're cleaning the system and that we're maintaining the temperature and humidity set points in a space. So while I think they're both interconnected, there's definitely a multitude of different approaches we take with each one. I'm sure Rob can add something there too.
Yeah, can you hear me, guys?
Gotcha.
Great. So what I'd like to say to that is, if you're going to be looking at airflow inside of a room, most likely it's going to be two separate systems that handle the conditioning of the air and the dehumidifying of the air. And I wouldn't rely on those systems to get the air just where it needs to be inside a very dense canopy inside the room. If you were trying to do that, you'd have ductwork everywhere. And frankly, these rooms can be quite busy. And you're just going to need some way to get air into the room, and then from the room itself or in a general cavity of the room out into the canopies in a way that's not going to impede the ability of people to get around the room, get in between the rows, et cetera, et cetera. But yeah, Jesse, everything you said was correct. And they're definitely very much intertwined.
Excellent. Thank you, guys. One follow-up question related to airflow is, what are some good vertical upward through the canopy airflow options as far as brand and style?
Well, shameless plug, oftentimes we don't see anything that's being done inside the rack and the tray to bring airflow through the canopy. And so we're often sourcing these and providing them ourselves. So we supply them. I think the most integrated system out there is probably the Vertical Air Solutions system, and that does a pretty good job. Now, I think the question was from the bottom up. Unfortunately, they only go from the top down at this point. But yeah, I think there are a number of options out on the market. You could reach out to us, and we'd be happy to tell you all about them.
And guys, just to piggyback on top of that, I saw a quick question come in about the effect that delivering this air directly to the stomata on the undersides of the plants, is that a potential stressor? And I think this comes back to a couple of things. It comes back to data collection and real world application. Absolutely, if we apply too much airflow too fast, we can affect the stomata negatively. We can get it to close, we can slow the plant's metabolic rate. So when it comes to this airflow delivery, it's really about making sure of two things: that the air is the appropriate temperature and humidity, so it's conditioned, and also that the rate of airflow, the actual velocity in which it's delivered to the plant, I think our studies show somewhere around a meter per second. I could be wrong on that, but we've done some in-depth data and studies, and just to show or just to get an idea of how much airflow we need to apply to that leaf surface to positively affect the plant, to break the boundary layer and deliver that CO2. without any stressors, without any leaf curl, without any negative reactions to the environment. And it's just key that that air is conditioned and delivered at the right velocity to avoid that kind of stress. Hopefully that's a little bit of insight on that concept.
Thanks, Jesse. Makes sense. Another question I have here is: does VPD and transpiration continue as a plant process post-harvest?
So this is Rob here. I think that the transpiration process does not. The transpiration is that full cycle. The water enters through the root system, up through the stem, and then out through the stomata of the leaves. At some point, when you've trimmed the plants, you've harvested it, that process stops. There are no more roots. There's no more water going through the stem. You're going to start seeing water leave the plant through the stomata or through that cuticular membrane on the leaves themselves. That is very much VPD dependent. Now, it's not a VPD chart you would use or find on the website I showed you before, but it's very much dependent on how much humidity is in the room, the temperature of the room, and the temperature and moisture content of the leaves. And those two things will play off each other. Those four things of the two subsets from the plant and the room, those things will play off each other and dramatically affect how quickly or how slowly that plant dries. And further, it'll affect the consistency of the drying. So many times we see a harvest lose so much value in the drying and curing process because it was dried inconsistently. It's crusty outside on the bud and a really moist interior that's just perfect for pathogen growth. And that right there is going to strip apart all the value you've put into that plant to that point.
Mm-hmm. Yeah, sounds like a great segue into our next webinar. More to come. Another question here. Can you provide a recommendation for maintaining soil temperature in large fabric beds?
Yeah, I think what we're really talking about here is, understanding the process of breakdown in those beds. What I'm picturing here is a no-till kind of approach where people are trying to maintain beds, or even just a soil recycling system where people are trying to sort of maintain the temperatures in those beds. And obviously we know that there's a pretty significant influence from the airflow and the temperature and humidity set points, how they're going to impact that soil. But I also think it's important to sort of think about the chemical breakdown and the nutrients that you're going with. If you have a soil-based program and you have a lot of really good organic inputs that are continually breaking down, and you have a lot of microbial activity, there's going to be a good chance that you have wonderful microclimates. This way, we're talking about microclimates in a good way, in that soil structure that allow certain fungal and bacterial colonies to thrive and spread their wings and sort of encapsulate those roots and protect them from some of the environmental threats. I also think it's important to think about water temperature. A lot of times we don't think about that delivery temperature, and if we deliver water that's really cold to a cold root zone when the lights are off, it's cold on cold on cold. And if we can deliver the water to the root zone after the lights have come on, we have a little bit of warmth in that room, we have a little bit of process going on in that plant. And if the water is warm enough but not too warm, again back to that Goldilocks porridge, we can use that to sort of maintain the soil temperature, or any media temperature for that matter as well. Hopefully that provides a little insight there.
And Brian, I'd like to add a little something too. Back when we were doing work in the mushroom industry, large soil beds were kind of the de facto standard for growing mushrooms inside of a cold, wet, dark room. And so maintaining those bed temperatures was pretty important. And some of the methods they use there, and I've seen some of this in the cannabis industry, people attempting it anyways, would be to use basically piping, a coiled piping, a radiant floor type system underneath the bed. You could put cool or hot water through it and end up with a temperature control scheme that way. And we've also seen people attempt to use phase change material, kind of novel. Now's probably not the time to get into it, but we've tried to see them use phase change material. I can't tell you how well it worked out. I can find out for you and let the person who asked the question know.
Great. Thank you very much. Stephen, I see that your hand is up and that you also have asked the question. I will try and ask your question here shortly. If you have more questions or follow-ups, I can also bring you on live to chat with us. So just let us know on that. The next question I'd like to ask is, indoor agriculture is very energy intensive. What are some ways to be more efficient with HVAC, and are there any sacrifices that are made to plant performance as a result?
Boy, you just threw me a soft one there, I guess. You know, at InSpire, we've designed and built some very efficient ways to dehumidify the air. The challenge is one of being able to use the energy you're putting into the system in a novel way. In standard dehumidification systems, they do that by using compressor energy to reheat the air after they've cooled it to that temperature where you get all the moisture out. We and some other manufacturers in the industry go a step further, and we will move the air from one spot to the other inside the air handling unit, in essence, pre-cooling the air before it hits the cooling coil, and using that same room energy to reheat the air back up. And effectively, we get 30 to 50% less compressor energy out of it. There are other very, very sophisticated ways, including desiccants, to increase the energy efficiency of the whole growing process. But you know, beyond all that, making smart light choices will probably help drive the efficiency of the facility. And also, we know that LED rooms, which are much warmer, have a much easier ability to dehumidify that air using less compressor tonnage. So those factors all combine, and from one to the other, we could see energy use 50% in an efficient building compared to a standard building, a legacy system that was, you know, being built and designed, I guess even today, but usually we saw them mostly, you know, 5 years ago or so. Does that answer your question? I hope it answers the person's question.
I believe so, but the second part would be, are there any sacrifices that are made to plant performance as a result of the more energy efficient process?
There can be, but that has more to do with the choices you make in general. If you don't have systems that can modulate and that can handle the cool times at night versus the hot times during the day and those transitions in between, it's the modulating equipment. If you're not using it, that's where you're going to find the challenges. It's one thing to throw a dump truck at it, but if you don't have a really effective gas pedal either on a dump truck or an efficient Prius, then you're not going to have a really good chance controlling those systems, and that's where the sacrifice comes in. I mean, the plant health will really suffer if you give those pests a place to thrive, if you're not doing the right thing for the root zone temperature, et cetera.
Yeah, I got it. I like that analogy. Very cool. Okay, got a question here from another attendee. Temperature, humidity, and airflow conditions can vary widely within a room. Is there an ideal room size for optimal quality? At what point does an increase in room size jeopardize plant quality? You guys have any sort of at least general ideas around room size?
Yeah, I mean, I think that, let me take a stab at this, Rob, and you can follow it up. I think for the most part, you know, as we've all transitioned to larger scale cultivation facilities, we've started to sort of appreciate the smaller room size for isolation purposes and, you know, prevention of spreads. But at the same time, you know, if you accurately and adequately understand your watering rate and you have an appropriate mechanical system, you can have a much larger scale. To me, it really comes down to a couple of things. It comes down to, you know, working with your engineer and really understanding the inputs and thoroughly vetting them and appropriate planning. But it also sort of comes down to CFD modeling, and computational fluid dynamics is something that, you know, I wasn't too familiar with until I really started looking at these larger scale rooms, and it wasn't as simple as, hey, we're going to put a fan every 6 feet. You know, this rule of thumb for traditional legacy growers was still applicable, but we needed to take those inputs and sort of take them to a data-driven science level And by doing the modeling, we're usually capable of determining, how many air exchanges we're going to have, per couple of minutes, or, where that air is going to flow, the potentiality for dead spots, and as a result, we can adjust our mechanical influences and cultural control in that space to make sure that we are controlling the space as a whole. A lot of times, traditional techniques are, let's put up some HVAC, let's put in some pocket dehumidifiers, and let's blow air all around the room. And I think what we're talking about is a recipe for microclimates. And without the appropriate planning and the appropriate data collection, it's really hard to get all those things on the same page and actually manage the envelope as a whole. But Rob, you have something you want to add to that?
Well, you basically stole my thunder. How dare you?
Yeah,
I was
boy.
going to say the exact same thing. Anecdotally, we see rooms 2,000 to 3,000 square foot, and then they might go 1 or 2 tier. We've seen some 4-tier rooms, but like you said, Jesse, without modeling, you can't really know. Modeling gives us a sheet that says what's the average dwell time of air inside of a room. It's one thing to design a room with an HVAC system that's going to do a certain number of air changes per hour, but even then, unless you can prove to me that we've gone in, modeled the canopy like they do in the wind tunnels, used those same formulas and applied them into the rows and the racks of the cannabis themselves through the CFD, I don't believe it. I need to see it to believe it. And that, modeling has helped us for sure.
Mm-hmm. Great. All right, the questions are coming in, guys. Thanks very much for the level of engagement here. Another question here from Eric Stutter, saying, I do energy studies of indoor cannabis facilities, and we've seen a lot of variety in how much dehumidification is required during flower dark periods. Does strain type have the most significant impact on dark period transpiration?
Wow, great question. I can tell you that we catalog every room that we design and go back to verify how much moisture is being taken out of it. Like you saw on that graph during our slide, we can measure the transpiration rate down to the minute, the instantaneous transpiration rate of the room. We have yet to catalog it by strain. So it's probably going to be the next thing we go and look at. Now, our rooms are generally designed on day one to handle a wide variety of plants. So we don't want to limit a grower or a facility to a specific strain on day one, and then 6 months later, market conditions change, et cetera. We always advise using standard rules of thumb and going just a little bit bigger than that for your room dehumidification design. But that being said, I can't wait to go back and look at that data. Very interesting. I'm curious to know.
Mm-hmm. Great. Hopefully that answers your question, Eric. Thank you again. I've got another question here from Jacob Hickey. Are there any fundamental strategies or differences in maintaining the 10 cardinal parameters in rock wool substrate?
Well, I think that's a really good question, and obviously that's an interesting conversation for a parameter. But your media choice is definitely going to have some impact on how you deal with it over the course of time and how your plant grows. So I think when you think about the 10 cardinal parameters, the importance is understanding the synergy and how they all interact and how they work together. And the same thing goes for your media choice. For example, if you're using a rock wool media, we know that initially that rock wool media tends to have a very high pH. It could be very high. It could be somewhere around 8. It could be even higher than that. So in understanding that and first appropriately treating the rock wool to get to that right pH is a step that you need to take because of your media choice in order to facilitate all those other parameters interacting, the microbe growth, the appropriate water retention, the right root growth that leads to plant vitality. And the same goes for every media choice that you have. They're all going to have slightly different considerations. Another one might be something like using cocoa. And we know that, cocoa has a tendency to bind nitrogen over a long period of time. So if you're recycling your media over years, that's something very important to consider. You might actually have to add more additional nitrogen to that product because you have a cocoa-based media. And then when you start to mix medias and build your own medias and build soil, you have all these other interacting factors as well. Some of them are buffers for success through that mixture, just by creating more inputs and more opportunities in the root zone. But absolutely, there will be an impact because of your media choice. Sort of mentioned temperature as well. So in a cloning environment, you have all these little rock wool cubes sitting around, and if you're blowing too much cold air past the environment, they're going to pick up that cold air. They're going to be sitting there without roots growing, and that's going to dramatically impact your ability to get roots quickly. But if you think about that and you raise the environmental conditions and deliver warmer air to that root zone that's oxygenated, that will have an impact on, initiating root growth faster. I think this is probably a topic for a much deeper dive, but hopefully that's a little bit of insight, and the answer is absolutely yes.
Great, thanks, Jesse. Another one here. I hear a lot about brute force HVAC. Are there any other options to consider?
Yeah, absolutely. I'll take this one. I mentioned the technologies before for dehumidification and how to make a less energy intensive growing operation. There's a number of dehumidification technologies. We call them in our products a coil runaround loop. There's an air-to-air heat exchanger around the same cooling coil mechanism that we talked about before. There are liquid and dry desiccant systems that can be used. When we talk about brute force, we're specifically talking about the use of a commercial air conditioner that takes the room temperature and humidity air and brings it all the way down past that dew point that's required to maintain the room condition. And that takes a lot of compressor energy. Compressor energy is 70 to 80% of most air conditioning systems. We try and reduce that using that air-to-air heat exchanger system or a coil runaround loop. And we've also looked at dry and liquid desiccants, and they might do a very good job too. Frankly, we haven't found much luck, but it's all about system design and thoughtful approaches ahead of time. Absolutely.
Excellent. Piggybacking on that question, in a region where outdoor temps can get below -30 degrees Fahrenheit and humidity in the 20% range, will this affect indoor conditions of an enclosed facility? And would concrete floors affect things as well?
Yeah, absolutely. I can tell you for sure that an unsealed, we'll start with the second question first. A concrete floor, we've seen it in rooms contributing humidity into the space, almost 50% of what the plants were doing at different times of the stages of growth. Especially this is a problem in drying rooms. So if you're going to use a concrete floor, your best chance to combat that and not have to over dehumidify moisture inside your space that's not coming from your plant is to seal it off. Use an epoxy seal. If the rest of the room is sealed, going back to the first part of the question, if the rest of the room is sealed and it's sealed very well and the pressure is controlled appropriately, then outside temperatures and humidities don't actually have that much of an influence. That outside air that's being brought in for ventilation purposes, if it's being brought in, and we recommend it should, especially for pressurization and pathogen control and biosecurity, well, that air should be treated. And if it's too dry, it should be moisturized. If it's too hot, it should be cooled down. We don't want to bring in air into a room that's not conditioned in any way, shape, or form. So we're going to have to manage that. It's an engineering equation. And at the end of the day, again, we recommend sealing rooms so that we have the best pressure control possible, if only for biosecurity reasons. That person can feel free to email me afterwards and I'll do a much deeper dive. But yeah, sealing a room, we find in most facilities we go into, we just don't have that much influence, even in the hottest desert areas of ambient conditions, considering the rooms themselves are rooms inside of facilities. So they don't have a solar load and there's very little thermal or humidity load inside the facility itself.
Mm-hmm. Great. Thanks, Rob. Circling back on the medium the question of medium. Are there any specific issues that InSpire can address if an aeroponic system is being utilized?
Yeah, I mean, I think when you think about aeroponics and the way that we're controlling the root zone, we don't have a buffer other than water, right? We're delivering a fine aerated nutrient mist to the root zone at periodic intervals, and water's being delivered through tubes and bucket systems that run throughout the facility. So when it comes to understanding the importance of that water temperature because it lacks a buffer, you know, we really need to control the oxygen levels in water and dilution of that delivery mechanism. So when the water runs through the systems and the pipes get hot and cold, those are going to have influences on the water delivery in the root zone. So in an aeroponic setting, it becomes of critical importance to control the ambient temperatures, to control the room temps, and make sure that you don't have dramatic spikes, that you can stabilize the delivery of that water throughout the entire propagation period. Does that make sense?
Yeah, that's great. Thank you. It looks like we have time for maybe one more question here. I'm circling back on the concept of drying rooms, which again, we'll take a much deeper dive on with our next webinar session. The question is, have you found an accurate way to estimate pounds per hour water loss of product in dry rooms on an hourly basis based on product mass, volume, percent moisture content, and or VPD? In turn, being able to accurately size the dry room HVAC system and control properly through the drying process.
Great question.
Yeah, I can take that one on. So I would say that, yeah, absolutely we have. Just like you saw in that graph with the red and blue bars, we can watch product in a room lose water weight at a certain pace based on the effective temperature and humidity control of that space. So starting at the beginning, if we can control the temperature and the humidity to the customer's desired requirements, that means we are removing the moisture that's coming off of the plants, off of the harvest, at a specified rate. But we use sensors that are accurate enough and have verified this with weighed product in the field, weighed over time, to know that our air conditioning system feeds back the moisture removal rate from the product itself. So we use our air conditioning system controllers to tell the growers and the harvesting team how much water is being lost on a pound per hour basis. That being said, we know that water starts at a certain moisture content, and the customer typically wants a targeted moisture content at the end of the drying process. What we do is we look at that difference in pounds of water coming out of the product and say, how many days do you want that product removed? How many days do you want that weight removed? And usually we end up with a number that's 7 to 10 days. You can make it go faster than 7 to 10 days by heating up the room, but you're probably going to do negative things to the plant. You can slow it down and really essentially slow down the plant drying process. These are all things that we play with, and it all goes back to really good sensors on the equipment that's doing the dehumidification and knowing from that exactly how that moisture loss is being handled.
Terrific. All right, hey, one more question, and we're going to have to sign off here in respect of everybody's time. For any of the questions that we didn't answer, please feel free to reach out to us directly, and we'd be happy to talk with you more. The final question here is, do you think recirculating molecular filtration equipment for odor mitigation has a negative effect on live cannabis in the space?
Say that one question one more time. Circulating.
Do you think recirculating molecular filtration equipment, such as activated carbon, for odor mitigation has a negative effect on the live cannabis in the space?
Oh, that's a pretty good question. I can tell you that we talked about VPD, which is, when we talked about it in this context, it was water vapor pressure deficit. I can tell you that there's also a vapor pressure for other products inside the cannabis, like the terpenes themselves, that if you remove them, you may end up causing a deficit of the terpene in the air, which would have a detrimental effect of the terpene on the plant, which is going to evaporate into the room. Now, how much carbon filtration do you have to use inside of a room to drop the vapor pressure down of a terpene to affect the plant? Don't know the answer to that. I can tell you that most times recirculated air isn't going through a carbon filtration scheme. In fact, it's only the air that's being ejected out of the room in the facilities we design that's going through carbon filtration. So the answer may or may not be yes. I don't think using carbon filters in your recirculating airstream is necessarily a good idea. The pressure drops are high. There's all sorts of other things that they're really going to impact your bottom line in a facility. That's how I'd answer that question. I hope I did answer it. Again, the person can reach out to me if they want. Jesse, do you have anything to add?
No, I think that was really good. I think when it comes to, recirculating, and it's better to make a really good stab at trying to do it right than, necessarily think about the minor implications that you might have for that recirculated air. We know that stale and stagnant air is going to be a health issue for people and plants and the like. And just like you mentioned, as far as an integrated system, it's probably looking more like some sort of capture filter, like a MERV 13, followed by some sort of secondary treatment, whether that's UV or photocatalytic oxidation or something like that, in order to make that recirculation path sort of make sense for a long period of time. The replacement on those carbon filters can be really tricky as well. You might run them for a couple of cycles and then not know if they're full and not know if you need to throw them away, and maybe not be able to accurately determine that. So I have my concerns with carbon as well, but I think you touched on that, Rob. We really just sort of use it as the exhaust odor mitigation, and we do some pre-filter before that for the integrated room system.
Excellent. All right, everybody. Looks like our time is up. We'd like to thank you all again for spending the last hour with us, and we look forward to having you participate in future events. Hope you all have a great day.
Thanks, everyone.
Yeah, thanks. Thanks, everybody.